Okay, this is an optimization problem. And optimization problems are problems in which we're trying to find the maximum or minimum volume of some quantity. In this case, we're trying to maximize the volume of a rectangular solid. Specifically, and this is important, a rectangular solid with a square base. All right, so let's draw a little sketch so we see what we're working with here. So we have a rectangular solid, so maybe something like this. Could give it some depth. Okay, so there we are. There's our rectangular solid. The base is square, so each of the four sides on the bottom and also on the top, let's call that x, and the height is possibly something else. We'll call that y. Okay, so we're looking for the dimension. So basically the question is saying, what is the length, the width, and the height of this rectangular solid under the constraint that the surface area is 13.5 square centimeters? And what length, width, and height will maximize the volume? All right, so volume of a rectangular solid is length times width times height. So we have V equals x times y, or x squared y. Now the problem is we have more than one variable, so if we were to keep both variables, well, this would be a calculus 3 problem, multivariable calculus, but since this is calculus 1, we have to express the function volume as a function of one variable. And to do that, we will use this piece of information here. The rectangular solid has a surface area of 13.5 square centimeters. Okay, so let's work with that over here. Surface area equals, well, let's see. We have the top, and that's x by x, so the area of the top is x squared, and same thing with the bottom is x squared. So we have 2x squared, that's the top and the bottom, and then we've got the four vertical sides, and that is x by y, so there are 4 of those, so 4x, y. And we're told that the surface area is 13.5. Okay, so so what we basically want to do here is we want to get rid of this guy. We want to get rid of the y. All right, so let's solve for y. Then we could do a little substitution. Okay, we could subtract the 2x squared from both sides. So we could say 4xy is equal to 13.5 minus 2x squared. And then we can divide both sides by 4x. All right, so we'll have y equals 13.5 minus 2x squared all over 4x. Okay, and so basically what we're going to do is take this, which is equal to y, and pop it in right here, which gives us a little bit more complicated looking function, but it's simpler in the sense that we have only one variable, volume in terms of one variable. All right, so we could say volume is now equal to x squared times 13.5 minus 2x squared, all divided by 4x. Okay, now let's do a little bit of simplifying here. One of these x's will cancel off with that x. So let's get rid of that. Okay, so we have volume is equal to 13.5x minus 2x to the third power, and each of these is divided by 4. And maybe if you want to pop those into the calculator to convert to decimal, that's perfectly fine. If you do 13.5 divided by 4, that should be 3.375x. And 2 divided by 4, that is 0.5x to the third. Okay, so now we have volume as a function of the length of one of the sides of the base. And to optimize this, so to maximize the volume, well, maximums and minimums, these could only happen at critical numbers. And a critical number is where the derivative is equal to 0. So we can go ahead, take the derivative, and that's the derivative of volume with respect to x. And that should be 3.375 minus 1.5x to the second. And we're going to take the derivative, set the derivative equal to 0. So let's get rid of that line over there. Okay. So we need 1.5x squared to be equal to 3.375. If we divide both sides by 1.5, we'll have x squared is equal to 2.25, and square root of both sides. In this case, we don't need the plus minus because x is a physical quantity that can't be negative, so we'll take only the principal root or the positive root, and that should be 1.5. And that's 1.5 centimeters. So if x is 1.5, the volume is maximized. Now we need all the dimensions. So we still need y. So we could take the 1.5, plug it in for x up here, and that will let us solve for y. And so it actually turns out that when we plug 1.5 in this equation up here, y is also equal to 1.5. So the dimensions, let me do it over here in blue. The dimensions of the rectangular solid that will maximize the volume are 1.5 by 1.5 by 1.5, or a perfect cube. Okay, that about does it for this one.